This video covers section 1.2, Applications of Propositional Logic. So one of the things that we need to become very good at is to be able to read a sentence and turn that into a propositional logic statement. So when we do this, what we want to do is look at our question, such as if I go to Harry's or to the country, I will not go shopping. So our job is to then determine what statements are we dealing with. So I go to Harry's is a statement. I go to the country would be a statement. And I go shopping would be a statement. Now notice I'm skipping the not for now because I will take care of that not with the not symbol when I actually write it. So notice here I've identified that I'm going to have three propositions, P, Q, and R. I go to Harry's, I go to the country, I will go shopping. And then we have to look at the connectives that we just learned in our last section. So it might be a good idea before you skip straight to this to try to think about it in terms of rewriting this with if P or Q, then not R. And so notice that's what I've done here. If P or Q, then not R. So I was looking directly at the sentence when I was thinking about that. And then from there, it's really not that difficult to translate it into a propositional statement with our logical connectives, because this would be P or Q. And then this, of course, tells me if then. So it's if P or Q, then, and then that's where we put in the not R. So here's the first one for you to try on your own. Remember, whenever you get to a blue title, I'd like you to press pause, try all the questions on the page, and then press play to see how you did. So here I have two for you to try. The first is you can access the internet from campus only if you are a computer science major or you are not a freshman. So we've got a lot of stuff going on here. So think about how you would like to assign those propositions. So accessing the internet would be one of our propositions. And then we also have you are a computer science major, and we have you are a freshman. And again, we won't worry about the not. So we could say P is campus internet access, Q is computer science major, R is you're a freshman. And again, you could be writing these and possibly using different variables for each, but same idea. And so notice here I'm saying P, or if P, then Q or not R. So if P, then Q or not R is how we would then write it. The second one, the automated reply cannot be sent when the file system is full. So we've got automated reply sent, and we have file system is full. So P could be automated reply can be sent, and Q, file system is full. And then notice we're saying if Q, then P. So if the file system is full, then the automated reply cannot be sent. And again, we don't negate it until we get to this step. Now let's take a look at whether or not a system is consistent. So a list of propositions is consistent if it's possible to assign truth values to the proposition variables so that each proposition is true. So essentially I'm saying I want all of these to be true, and I need to be able to assign my P and Q in a certain way and assign truth values to that P and that Q in order for all of these statements to be true. So let's first take a look at the propositions that we should use. So we have a diagnostic message is stored in the buffer, or it is retransmitted. So that essentially, I'm going to go ahead and continue my underline. So it's either stored in the buffer or it's retransmitted. So that's how we're going to use our P and our Q. And again, we can do the same thing here. Diagnostic message is not stored in the buffer, and that one doesn't have anything to do with Q being retransmitted. Or if the diagnostic message is stored in the buffer, then it is retransmitted. So essentially, I want to take each of those and then turn them into propositional statements. So looking at the first one, the diagnostic message is stored in the buffer or it is retransmitted. So or, of course, looks like this. So we've got P or Q. Then we look at the second one. The diagnostic message is not stored in the buffer. So again, that tells me my not P, because P represented stored in the buffer. And the last one, we've got an if, then, and of course that gives us our arrow. So if P, then Q. So once we get to this point, now we have to look at, can we assign a truth value to P and a truth value to Q so that the truth value of P or Q, or not P, or P, if P then Q, would all be true. And if we say that P is false and Q is true, so again, P is false, which would be not false, which would be true. And this one is if false, then true. And of course, looking at the truth value of this statement, oops, I used Q there instead of T, sorry. So if I look at the truth value of false or true, that is true. If I look at the truth value of not false, that is true. If I look at the truth value of if something's false, then true, we know this is that tricky one where it starts with a false, it's true. So this is a consistent, all of the specifications are consistent because we can assign the truth values to make all of the statements true. We're now going to shift focus a little bit to logic puzzles, and logic puzzles are absolutely an application of propositional statements. And the first one we're going to look at is one that is very well known, and you'll see different versions of this or different statements that are involved in each version, but there are quite a few logic puzzles involving knights and knaves. So for our first one, it says an island has two kinds of inhabitants, knights who always tell the truth and knaves who always lie. You go to the island and meet A and B. A says B is a knight. B says the two of us are opposite types. And the question is, what are A and B? Are they both knights, both knaves, one of each? How does it work out? So let's let P represent that A is a knight and Q represent that B is a knight. Now it is possible to create a truth table for this, but honestly on a question like this, I think it's easier to just use logic rather than to use necessarily those prepositional statements that we're talking about. For instance, if I just reason through it, I can say, let's assume A is a knight. So remember, we've really got that A is a knight and B is a knight. We have that A is a knight and B is not a knight, which would be a knave. We have that A is not a knight and B is a knight, or A is not a knight and B is not a knight. So those are our four options. So keep that in mind as we're moving, or I guess these should be P, since we said P was that A is a knight, and this should be Q. So we said suppose A is a knight, so I'm supposing that it's one of these two. So the tricky part here is that because A is a knight, A is telling the truth, and A told us that B is a knight. So that means B must be a knight. But B said A and B are of different types, and if this guy is also a knight, he had to have been telling the truth, and so there's something wrong. The logic doesn't work. So it is not possible. Either of those scenarios are not possible. So then we look at the fact that A could be a knave. So if A is a knave, he tells us that B is a knight. Now, being that he is a knave, he's lying. So that tells us that B is a knave. B tells us that he and A are of different type. And of course, because he's a knave, he has to be lying, which means A and B have to be of the same type. And therefore, this logic holds not Q and not P, because both A and B are knaves, and that's the only logical conclusion. So this is one way to solve this knights-knaves problem. Now, as I said, it is possible to do this with the truth table, and sometimes using P and Q might get a little bit confusing, or it might be easy to, get yourself going down the wrong track. So here it is in a little bit different type of way. So just another way I could represent this. And notice here, this is essentially what I had at the top of the last screen, except I was using P and Q, or not P and not Q, etc. So then we look at the statements essentially that we are given, that A says B is a knight. So if A says B is a knight, then, and A is a knight, then this guy must be a knight because he's telling the truth. And so what I'm looking for here is I want whatever happens in this column to be the same as what happens in this column. That is my end goal. So now I'm saying A is a knight. Well, B must be a knight because he's telling the truth. If A is a knave, then B must be a, let's see, oh, I just got myself confused. If A is a knave, he's telling a lie, which means this guy must be also a knave. And same thing is going to happen here. Okay, so we haven't really figured anything out yet. We're just filling in values on the table. Then it says B says the two of us are opposite type. So if B is a knight, he's telling the truth, and this guy must be a knave. So we can see that this is knight, knight, which matches what I had over here, but this is knave, knight, and so this one's not going to work. Let's look at the next row. B is a knave. B said the two of us are opposite types, so he's lying. So this guy's a knave. This is knave, knave. This is knight, knight. These don't match, and they don't match what I started with either, so that row is not going to work. Then we take a look at the next one. If B is a knight, then he is telling us the truth, and A must be a knave. So we have knave, knight. Over here I have knave, knave, and therefore those don't match up, and that is not a valid solution. And looking at the last one, B is a knave. He's telling me a lie in saying that they're opposite types, so A must be a knave. So now I have knave, knave. Looking at this row, or this column, I have knave, knave, and here I have knave, knave. Because it worked out the same for my original statement, and after each of the other statements, that is the only way that this could work logically. I have another question I'd like you to try, and this one is straight out of your textbook, page 23, number 18. And for this one, just to give you an idea of how we could write a truth table to help us solve this, I did solve this one with a truth table, but don't feel like you are tied to that method. I'm going to read this question with you, and then I want you to press pause, and I want you to really take the time to try this question before you look at the solution. So when planning a party, you want to know whom to invite. Among the people you would like to invite are 3 touchy friends. You know that if Jasmine attends, she will become unhappy if Samir is there. Samir will attend only if Kanti will be there, and Kanti will not attend unless Jasmine also does. Which combinations of these 3 friends can you invite so as not to make someone unhappy? So for the sake of uniformity, if you choose to make a truth table, just use J for Jasmine attends, S for Samir attends, and K for Kanti attends. So go ahead and press pause. Try this question, take your time on it. It might take you a little while. It might just be really easy for you and you get it right away. Once you're done, press play to see how you did. So what I did, what I did was I looked at all of the possibilities, because essentially what I have is three propositional statements, and we know that 2 to the third would be the number of rows that I need. So that's what I did first, is just to make all of the possibilities. Then for each one, I looked at the statements given to me in the question. So it says, if Jasmine attends, she will become unhappy if Samir is there. And so notice I wrote, if Jasmine, then not Samir. That is this column. Then I looked at, Samir will attend only if Kanti will be there. And so if Samir, then Kanti. And then my last one, Kanti will not attend unless Jasmine also does. So again, if Kanti, then Jasmine. And essentially what I'm doing is I'm doing it the exact same way that I did the last question, except on the last question I didn't use propositional statements or letters. I just used knight and knave, but it's really the same idea. So without going through step by step with you, essentially what I was doing is I was looking for any rows where the three values were the same. So here, this one didn't work. I had JSK, and obviously this one was not S, and so we were done. Here I had JS not K, and right away we can see we've got a problem using the information that's given. One thing I should point out, because maybe I didn't make that clear on the last question, for the K values, I want you to notice here that K isn't involved in anything here. So notice all I did was I took the K directly over. And for the J column, I took the J directly over because I'm determining what's happening with S based on J. So the only thing that I'm figuring out in this one is what's happening with S. Hopefully that is clear. Same thing if I'm looking at the blue column, that if S then K. I better put my purple star back up there so we don't get confused. So if I'm looking at the blue column, if S then K, remember J is not changing at all, and S is not changing at all. I'm just basically transferring those over from what I had before. K is changing because it's changing based on the value of S. So again, I continued that for all three of the different statements that I found. And so what I found at the end is that I can either invite Jasmine and Kanti, or just Jasmine, or essentially I can invite no one. So this one worked out just fine, where we can see all of those sets of three are the same. I said we could invite Jasmine, Kanti, and that is this row right here. So Jasmine and Kanti got to go, but Samir did not. I can invite just Jasmine, so J, but not the other two, and that's this row right here. And again, what I was looking for is each set of three to be the same. Let's take a look at this last logic question. I want you to use whatever method that you like best. So whether that is making a truth table or just reasoning it out, use whichever method that you like best. When you are all done, press play, check your work to see how you did. So before we get started, let's take a look at our suspects. We have Mr. Smith, and Mr. Smith tells us that Cooper was a friend of Jones and Williams disliked him. We also know Jones, and Jones doesn't know Cooper, and that he was out of town the day Cooper was killed. And then we have Williams, and Williams states that he saw both Smith and Jones with Cooper the day of the killing, and therefore it must be one of them. Now, of course we know there are only three options. And so essentially we pick one and see if the logic works. So let's start with Williams. If Williams is the killer, then what? Well, if Williams is the killer, then that means Smith and Jones are telling the truth. Smith says Cooper is a friend of Jones, and Jones says he didn't know Cooper. So those two don't work because Cooper can't be a friend of Jones and then know that they don't know each other. So Williams is not going to be our killer. So let's take a look at Smith. If Smith is the killer, then we know Jones and Williams are telling the truth. Jones says he doesn't know Cooper and he was out of town the day Cooper was killed. Williams says Smith and Jones were with Cooper. So again, these two don't work because if Jones doesn't know Cooper, then he couldn't have been with Cooper the day he was killed. So Jones, it isn't looking good for you, buddy, but let's go ahead and see if the logic works. Mr. Jones is the killer. That means Smith and Williams are telling the truth. Smith says Cooper's a friend of Jones and Williams dislikes him. And Williams says Smith and Jones were with Cooper the day of the killing, and therefore one of them must be the killer. And so those two do not contradict one another. Therefore, it's very possible that Jones was with Cooper the day he was killed, and he was the killer. So I have it all written out nicely for you, but I wanted to talk through it with you. So here's our three options, and of course we decide that Jones is the killer. So your assignment is to complete the rest of the assignment for sections 1.1 and 1.2. Notice I've given you a couple of odd questions, but I've also given you some even questions. So these questions do take a little bit longer. What I'm looking for is for you to either show me a truth table or be able to explain it in a way that is clear and makes sense and that I can follow your reasoning.